Hello guys, welcome back. We are jumping into part 2 now of our exercise set here in 1.1, first section of chapter 1 here in our geometry full course. So let's jump right back in. We're at the practice and problem solving portion. We'll begin with numbers 13 through 15 here. Alright, use the figure to name each of the following. Question 13 asks for 3 collinear points from our figure here. So let's jump over here. We have B, E, A. They all lie on the same line. So we can trace the line here through B, E, A. On the figure, we can write next to question 13, B, E, A. All right, let's continue on to number 14. 4 coplanar points. 4 points that all lie on the same plane, in other words. So let's go back to our plane here. B, C, D, E. Now that includes all lying inside of the parallelogram, or the plane here. So our possible answer here is B, C, D, E. Question 15, a plane containing E. Now the parallelogram in the figure here contains E, and we can name it by any 3 of its non-collinear points, for example, A, B, and C. All right, so A, B, C is our possible answer. On to the next part. Draw and label each of the following. Number 16, a line containing X and Y. So we have 2 dots here labeled X and Y, with a straight line going through both of them with arrows at both ends. All right, so again on question 16, you'd want to draw a straight horizontal line, mark a dot near the left and label it X, mark a second dot near the right and label it Y, and then put arrows on both ends. Now above the drawing, we can write line XY. With our arrows at the end. A double-headed arrow on top. All right, so again, this is a straight line through points X and Y, arrows on both ends. We can name that line XY. Now 17 is asking for a pair of opposite rays that both contain R. So here we'll have a horizontal line with R in the middle. 2 more dots, one on each side of R, arrows on both ends. The 2 arrows from R go in opposite directions. So why don't we go ahead and make our second dot here. We'll call that one A, and our third dot here and call that one B. So for example, we have ray RA, and we have ray RB. Each here with a single right pointing arrow on top. So a horizontal line with R as the middle point and arrows going both directions. The 2 rays are named ray R left point and ray RA for our left point and ray RB for our right point. These are just some examples that we could use A and B. Of course, you can use any letters that you like. Let's just make sure order matters here in our rays. We do want to start with our endpoint R, always. Start with the endpoint for rays. R must be the first letter in this particular line of each ray name because R is the common endpoint. All right, let's continue on. Use the figure to name each of the following. 18, 2 points in a line that lie in plane T. Let's zoom in on our figure here. There is plane T. Let's see where our points are. We have G, J, line L, and that will work. G, J, and line L there. Number 19, two planes that contain L. Let's look carefully at our figure. Line L runs along the bottom edge of plane S. So it lies on plane S. And it also lies on plane T. It's drawn flat on the horizontal plane there. So two planes that contain line L are plane T and plane S. Planes T and S. All right, on to 20 and 21. 20, a line that intersects two non-intersecting planes. Let's take a look at our figure. So we want two parallel-looking planes, one above the other, with one line going through both of them like a skewer. Here below 20, we can draw an upper parallelogram. That will be our top plane. And then our lower parallelogram will be our bottom plane. These are drawn parallel to each other. One straight vertical line that pierces both planes with arrows on both ends. Check. And we'll mark the 2 points where the line hits each plane. All right, so two parallelograms. The two planes do not touch each other. They're parallel, and a single straight line going through both. Think of it as like a kebab skewer just going through both two parallel slices here. And 21, three coplanar lines that intersect in 3 different points. Let's take a look at our figure for 21. So here we want 3 lines drawn so that each pair crosses at a different spot, like the 3 sides of a triangle, but they'll be extended into full lines with arrows on the ends. So we'll draw a parallelogram, the plane. Inside the plane, we draw those 3 straight lines that cross each other. So each pair of lines meets in a different spot. And we can mark the 3 intersection points with circles if we'd like. A simple way to do this would be, for example, to just go ahead and draw your triangle. And then from there, you can extend each side into a full line with arrows on both ends, like such. Here's a line. There's a line. And here's another line. All going through our triangle here, and then our points make our triangle. So in other words, the 3 extended sides will cross at the 3 triangle vertices. All right, so again, 3 straight lines drawn in one plane, such that each pair of lines crosses in a different point. The simplest version looks like a triangle with each side extended into a full line. 3 intersection points in total. All right, guys, let's continue on to number 22. This is a test prep question. All right, let's take a look at our visual. This is a photo of an archaeological dig site. Now, the dig site has wooden stakes pushed into the ground. Let me circle those so they're easier to see. Now, strings are tied between them. Like such. And this forms a square grid laid over the dirt. Now we're asked to name an object at the dig site that is represented by each of the following: a point, a segment, and a plane. So let me erase this part. All right, so part A is a point. A point will name a single location with no size. So at the dig site, the tip of a stake is a real-world example of a point. It marks just one specific point in the dirt. Let's label that as such. 22A, tip of a stake. Whoops, not that stake. Maybe I'm thinking of food at the moment. All right, so a possible answer is the tip of a steak. All right, on to B, a segment. Now, a segment is a piece of a line with two endpoints, as we've learned. So at our dig site here, each piece of string tied between two stakes would be a segment, for example. It has a clear start, one stake, and a clear end, the other stake. So we can write next to 22B a string between two stakes. There's that string. A string between two stakes. 22A was a tip of a stake. And now 22C is a plane. Now, a plane is a flat surface, so at the dig site here, the entire square grid formed by the strings stretched between the stakes lies on a flat surface, so that grid would represent a plane. We can draw that out. There's our plane. So my answer would be the grid formed by the string. All right, let's continue on. Draw each of the following. For 23 and 24, we'll have a visual here, a little diagram. All right, so plane H containing two lines that intersect at M. Let's zoom in. Here's our plane H, our two lines that intersect at M. All right, so again, below question 23 here, we're going to draw a parallelogram, which is the plane. We'll label that parallelogram with our script H, or just write H if you can't make a script, that's fine. And inside the plane, draw two straight lines with arrows on both ends of each that cross at one single point, and we'll label that crossing point M. All right, and now we're on to 24. Line ST intersecting plane M at R. All right, let's take a look at our figure over here. For 24, we have plane M at R. So let me fill that in a little where it's coming out. This is M, plane M. And we have line ST intersecting through R there. Put our points in there. All right, so again, we have a parallelogram here. The plane, labeled here plane M, and we're drawing that slanted line that pierces the plane through one point. Label the point on the line above the plane S, and the point on the line below the plane T, with arrows on both far ends of the line. And where the line crosses the plane, we'll place a dot and label it R. All right, so again, a parallelogram labeled plane M with a slanted line ST that passes through it. The point of intersection is labeled R. Let's go on to 25. We have another figure over here. Here's our figure. We're looking at the intersection of line TV and ray US. All right, here is TV, line TV, and then here is ray US. And we can see the intersection there is indeed U. Now we have the intersection of ray US and plane R. Back to US. There's our ray US. This is our plane R. So again, U. So line US, ray US starts at U on the plane and it goes up to S above the plane. So the only place it touches on the plane is at U. And 27, the intersection of segment TU and segment UV. Let's take a look a little closer at our figure. Put a dot there. Here is that segment. segment TU, and then segment UV. And again, they share the endpoint U. So U for all three answers. All right, let's take a look at 28. Write the postulate that justifies each statement. 28, the line connecting two dots on a sheet of paper lies on the same sheet of paper as the dots. Oh, right. This will go back to our other video. This will be postulate 113. If 2 points lie in a plane, then the line containing those points lies in the plane. So postulate 113. 29. If two ants are walking in straight lines but in different directions, their paths cannot cross more than once. All right, this will take us to postulate 114. If two lines intersect, they intersect in exactly one point. All right, now we have a critical thinking question for number 30. Is it possible to draw 3 points that are non-coplanar? Explain. So we'll give our why or why not here. Now the answer is no, it is not possible. And we'll refer back to postulate 112 for our why. 112 says that any 3 non-collinear points are contained in exactly one plane. So 3 points that are not on the same plane will always be coplanar. And if the 3 points are on the same line, then many planes pass through that line. So they're still coplanar. But either way, 3 points are always coplanar. And I won't take the time to write all that down for the critical thinking question, but you could write a whole paragraph there to explain that. So again, it's not possible by postulate 112, any 3 non-collinear points are contained in exactly one plane. If the 3 points are collinear, then they're contained in infinitely many planes, but in either case, the 3 points are coplanar. Now for our next set here, 31 through 38, which will end our video and our review. Tell whether each statement is sometimes, always, or never true. Support your answer with a sketch. So let's begin with 31. If 2 planes intersect, they intersect in a straight line. All right, so this is exactly postulate 115. Whenever 2 planes intersect, they intersect in exactly one straight line every time. So the answer is always. Let's take a look at our sketch for 31. And on this one, we really could have drawn 2 parallelograms crossing each other with a dashed line where they meet, which was the same as example 4, part B, or this will work as well. But the answer is always. 32, if 2 lines intersect, they intersect at 2 different points. Here we'll refer back to 114, which says that when 2 lines intersect, they intersect at exactly 1 point, never at 2. So the answer is never. Let's take a look at our figure. Here we want to sketch 2 straight lines crossing at one single point, like in the figure 32. All right, so 32 is never. 33, line AB is another name for line BA. Yes, always. Now let's take a look at 33. Here is our sketch that go infinitely in either direction, so we can write them either way. And the same with the segment as well. This is a line though. But notice our segment could also be AB or BA. All right, so 33 is always. 34, if 2 rays share a common endpoint, then they form a line. We'll take a closer look at 34 here. 2 rays from the same endpoint form a line only if they go in exactly opposite directions. Those would be called opposite rays in geometry. So if they go in any other directions, for example, if they make an angle, which we'll be discussing quite a bit angles in this class, in this course, I mean, they don't form a line if they make an angle. They form an angle. So sometimes yes and sometimes no. The answer is sometimes. Let's take a look at our sketch. There's an angle, there's a line. So sometimes. 35. Art. Pointillism is a technique in which tiny dots of complementary colors are combined to form a picture. Which postulate ensures that a line connecting two of these points also lies in the plane containing the points? Or in other words, the canvas. So this is postulate 113. If 2 points lie in a plane, the line through them lies in that plane. Postulate 113. All right, 36 is probability. 3 of the labeled points are chosen at random. What is the probability that they are collinear? All right, so 3 of the 4 labeled points, A, B, C, D, are picked at random. So we're going to count how many ways we can pick 3 of the 4 points, right? So for example, we have ABC, ABD, ACD, BCD. All right. So that's 4 different groups, 1, 2, 3, 4. And now we can count how many of those groups are collinear. Now looking at the figure, A, B, and C are only 3 points on the straight line. So only the group A, B, C is collinear. That is one group. So probability is favorable outcomes divided by total outcomes. That would be 1 out of 4, in other words, or 1/4. So 1/4. 37. Campers often use a cooking stove with 3 legs. Which postulate explains why they might prefer this design to a stove that has 4 legs? Now we talked about the 3 versus 4 points in our previous video, but we're looking at postulate 112. 3 non-collinear points determine exactly one plane, so 3 legs always sit flat. A 4th leg might not match the same plane, for example, so it could wobble. All right, postulate 112. And now we're at write about it. I'm not going to write this all out, but we will discuss it. This will be our last problem in 1.1. Explain why 3 coplanar lines may have 0, 1, 2, or 3 points of intersection. Support your answer with a sketch. Let's go take a look at our answer from the text. All right, so 3 lines on the same flat surface can be arranged in 4 different ways, as we see here. 0 intersections if all 3 lines are parallel or never crossing. There are 0 intersection points. 1 intersection if all 3 lines pass through the same point, like spokes on a wheel. There is 1 shared point of intersection. 2 intersections if 2 of the lines are parallel and a 3rd line crosses both of them. There are 2 intersection points as such. And then 3 intersections if every pair of lines crosses at a different spot, like the 3 extended sides of a triangle. There are 3 intersection points. If we zoom in, there's our triangle. All right, so 3 coplanar lines can intersect in 0, 1, 2, or 3 points depending on their arrangement. All parallel are 0, all through one common point would be 1, 2 parallel with 1 transversal would be 2, and each pair crosses separately and makes 3. All right, guys. Thanks for sticking with me through the video today, and we will be jumping into our next section in Chapter 1. So I will see you guys soon. Take care. Bye.